Welcome to this video on error detection. In data communication, it is important to make sure the information sent by the sender reaches the receiver accurately. However, the noise and interference in the transmission medium can cause errors during data transfers. Error detection helps identify whether the received data has been changed or damaged during transmission. It does not fix the error but helps in detecting it so that corrective action can be taken. Common error detection methods include parity check, cyclic redundancy check, and checksum, all used to verify accuracy and integrity of the transmitted data. These techniques help maintain reliable communication even over unreliable networks. When an electromagnetic signal travels from one point to another, it is often affected by interference from heat, magnetism, or other electrical disturbances. This interference can distort the shape of the signal. When such a signal carries binary data, even small distortions can change the meaning of the data, resulting in errors. Errors are generally classified into two types: single bit error and burst error. Single bit error occurs when only one bit in a data unit, such as a byte or packet, changes from 0 to 1 or from 1 to 0. A first error occurs when two or more bits in the same data units are altered, making it more complex to detect and correct. Once data is transmitted from the sender to receiver, it is important to check whether the received data is error-free. To do this, we use several error detection techniques that help identify any changes that may have occurred during transmission. Some commonly used methods are parity check, CRC or cyclic redundancy check, and checksum. Each of these methods play a key role in ensuring the accuracy and reliability of data communication. VRC or vertical redundancy check is one of the simplest and earlier error detection techniques. In this method, an extra bit called the parity bit is added to the each data unit to make the total numbers of ones either even or odd depending upon the parity scheme used. VRC is effective in detecting single bit errors, ensuring that even small transmission faults are caught. However, it can only detect first errors if the total number of bits changed is odd. If an even number of bits are corrupted, the error may go undetected. Thus, while VRC is simple and efficient for small data units, it is not suitable for detecting multiple or complex errors in large transmissions. LRC is an error detection technique designed to increase the likelihood of detecting burst errors, which are common during data transmission. In these methods, data bits are arranged in table format with each row representing a data unit. A parity bit is calculated for each column and added as an extra row known as the LRC block. At the receiver's end, the same parity checks are performed to verify data integrity. Although LRC is better than simple parity checks at the detecting burst errors, it still has a limitation. If two bits in one data unit and two bits in the same positions in another data units are damaged, the error may go undetected. Overall, LRC improves error detection reliability but is not completely foolproof. The most powerful redundancy checking technique is CRC. Unlike LRC and VRC, which use binary addition, CRC works on the principle of binary division. Here's how it works. A sequence of extra bits called the CRC remainder is generated and appended to the end of the data unit. This ensures that the combined data becomes exactly divisible by a predefined number called the divisor. At the receiver's end, the same division is performed again. If the remainder is 0, the data is considered error-free and accepted. If a remainder exceeds, it indicates that an error occurred during transmission and the data is rejected. CRC is highly reliable and widely used in networks and storage systems to ensure data integrity. First, a string of 0 is appended to the original data unit. The number of zeros added is 1 less than the number of bits in the divisor, which means n zeros for a divisor of n plus 1 bits. Next, this extended data is divided by the divisor using modulo 2 binary division. The remainder is then appended to the original data, replacing the appended zeros, forming the final transmittable data unit. When the receiver gets this data, it performs same division using the same divisor. If the remainder is 0, it means the data is error-free and accepted. If the remainder is non-zero, it indicates that an error occurred during transmission and the data is rejected. This method provides a powerful and reliable way to detect transmission errors in digital communication systems. Suppose the sender wants to transmit the information string 1111101. Both the sender and the receiver agree to use the polynomial pattern 1101 as the divisor. The sender first appends the three zeros to the data. Since the divisor has 4 bits, the new data becomes 1111101000. Next, the sender performs modulo 2 division of this data by the divisor 1101. The remainder obtained from this division is 0111. This remainder is then added to the data unit, replacing the appended zeros. So the final transmitted code word becomes 1111101111. When the receiver gets this code word, it divides the entire sequence by the same divisor 1101. If the remainder is 0, it confirms that the data is error-free. If not, it means an error occurred during transmission. This example clearly shows how CRC ensures data integrity using simple binary division. Checksum works on the concept of redundancy just like other error detection methods. At the sender's end, a command called the checksum generator processes the data. The data unit is divided into equal segments of n bits, typically 16 bits each. These segments are then added together using one's complement arithmetic so that the total remains n bits long. Next, this total is complemented and the resulting value is appended to the end of the original data. This extra set of bits is known as checksum. The checksum serves as the redundancy check, helping the receiver to detect if any data corruption has occurred during transmission. Let us see how the checksum is generated at the sender side. At the sender, the data unit is first divided into k section, each contains n bits. All these sections are then added together using one's complement arithmetic to get the sum. Next, this sum is complemented and the result becomes the checksum. Finally, the checksum is appended to the original data and sent to the receiver. This simple and effective process helps ensure that any errors during transmission can be detected at the receiving end. At the receiver, the data unit is divided into k sections, each containing n bits. All these sections are then added together using one's complement arithmetic to obtain the sum. Next, the sum is complemented. If the result is 0, it means the data has been received error-free and is accepted. If the result is non-zero, it indicates an error during transmission and the data is rejected.